welcome to the lecture on Introduction to Strengthening Mechanism in Metals. So, we will discuss about the mechanism of strengthening which is there in the case of metals or alloys, and we all know that we need strong and stronger materials for use in engineering applications. And normally what we do is normally we are deforming the materials, and at some point of time when we are giving the load, when the material is subjected to any load, then at some point it will start deforming. So, you have to do certain measures to increase its strength, and what are those mechanisms by which you can make the material stronger, and what will be the concepts behind them, or what are the prerequisites to be studied for that. So, in this lecture we are going to discuss something about it. And the ability of material to plastically deform depends on ability of dislocations to move. So, basically you know that dislocations are moving, and that means that the material has plastically deformed. And also if by some mechanism or by some techniques we are restricting these dislocation movements, it means basically we are going to make the material harder and stronger. So, if you talk about the different methods of making the material stronger or harder, so in the metallurgy or material science we are going to talk about few of the methods, and these are like grain boundary strengthening. So, as we know that grain boundaries are there where when the dislocation is there, so it will have the resistance to cross the grain boundaries. So, by increasing the number of grain boundaries, or by in fact that is achieved by increasing the number of grains. So, that way you are strengthening the material. So, as we know that we have many techniques for increasing the number of grains, like while casting you can have the different mold materials. So, we have different mold materials, like we have commonly used mold material is sand, and if you go for the metallic mold, then the cooling rate is higher. So, you are going to have the finer grain structure. So, that way the material which you get by cooling in the metallic mold, so that will provide you more number of grains. So, you will have in that case you have the strengthening developed, and basically you have certain correlations which are given by which tells that if the number of grains are increasing or the grain size, average grain size is decreasing, in that case the stress required to move the dislocation will be increased. So, if your number of grains are more, then stress required to move the dislocation will be higher, and if it is less, then in that case it will be less. So, that is the concept of grain boundary strengthening. Similarly, you have cold working. Cold working or strain hardening, basically in one case they are same. So, cold working is another method where basically the material is cold worked, material is worked below the recrystallization temperature, and in that basically the dislocation density is increasing, and it is seen that when the dislocation density will increase, then the stress again required to move the dislocation will be higher, the yield strength will be higher. So, cold working is another method to strengthen the material, and as we might have seen practically at many occasions that when a material is cold worked, or even the typical example of that will be if you have a mild steel rod, and if you are trying to bend it and unbend it many number of times, then at one point of time it breaks. So, before that it becomes harder and harder, and at one point of time then it becomes brittle, and then so it breaks. So, using these cold working methods also you can have the increase in the strength. So, it is also a strengthening mechanism. Martensite strengthening, so this is basically because of the transformation product martensite, and we know that we have studied that now when we are decreasing, I mean when we are increasing basically the cooling rate. So, in that case after a certain critical cooling rate, if the cooling rate is more than that, in that case you are getting martensite, and basically martensite formation is because of the shear induced phenomena. So, it is a diffusionless transformation. So, in that case what happens, the large amount of stresses accumulate, and so you have strengthening achieved in that case. Similarly is the strain hardening. So, similarly that as you know that when we strain, it will be strain hardening induced in the metal, and then that way the stress required to move the dislocation will be higher. Fiber strengthening is another method, because in many cases you use the fibers, and fibers will have more rigidity, more strength than the parent matrix. So, fiber strengthening is another mechanism by which you can make the material stronger. So, very much vivid example will be the case of composite materials, where we have the parent matrix will be the ductile material, and then we also use the fiber materials. So, the fibers are the materials with high rigidity, and they have high stiffness, basically same stiffness and rigidity, and then its materials the materials property increases. Solid solution strengthening, it is based on the concept that when we make solid solution, and if you have the atoms so you will have interatomic distances or interatomic voids in fact, and if you try to alloy with the material which is very much smaller in size, but then its size is more than the voids which is there in between the atoms. In that case, if you are able to trap these small sized materials into the matrix, so that will produce a stress field, and it will be resisting it will be giving you a stress field, and the material will have the better properties. You will require higher stress for the material to deform. Another method which we will discuss will be strain edging. So, that is another phenomena where it was seen that if you load the material, unload the material, and then further if you do some heating and then you further do the loading. So, that way also some other phenomena, kind of a phenomena is observed, increase in strength is observed. So, yield point is increased. So, this kind of phenomena is observed in some of the materials. So, that is strain edging. So, because of the edging treatment or in heating to a lower temperature, that results into. So, basically these are the different strengthening approaches, and we should know that first of all we will have a light on the concepts about how the material becomes harder, what makes the material harder, and as we discussed that the strengthening techniques rely on restricting the dislocations movements. So, basically what happens that you have, when you have the plastic deformation, then plastic deformation will be by many mechanisms. So, what is the concept of that plastic deformation, and then what are the modes of the deformation, and then when you deform, then how how this shear stress value has to be calculated, and how it is a function of the shear modulus of the material, and how they differ from the actual, and I mean there is difference between actual and the theoretical values. So, on that we will be having certain light. So, as you know that if you talk about the plastic deformation, So, so what we see that in the case of plastic deformation, you have that is analyzed normally using the load elongation curve or using the true stress true strain curve. So, you must have seen the proper load elongation curve. So, as you know that when you typically draw the load elongation curve for a ductile material, so the load elongation curve goes, so you will have a straight region and then it moves. So, that way it goes so what you see that and after that it will go on decreasing also after some certain time. So, if you normally you have a load and elongation curve. So, this is, or what we do is in that we also call it as a stress strain diagram, that is engineering stress engineering strain curve. So, what we do is we normally divide it with its original area. So, you will have engineering stress and engineering strain, and then that value is calculated. So, if at any point P is the load, so P by A naught will be engineering stress. Similarly, the length change in length upon original length, so that will be your engineering strain. So, that way you will have such kind of, so one of the diagram is that, and the maximum point will be the ultimate tensile strength, and then you will have one is a proportional limit, because up to certain point the stress will be proportional to strain, and then after that so you give a certain value of the yielding, and that will be proof value, and for that basically you define the yield point, and then the maximum value will be the UTS. So, that's what is the load elongation curve. Now, in this case what happens that after this point basically there is necking starting, and then there will be basically the permanent deformation starts, and also as there is permanent deformation increase in the length. So, certainly decrease in the cross sectional area will be there. So, because in the plastic deformation region your volumetric volume constant condition will also be maintained. So, you will have the change in the cross sectional area, and ultimately after that time after this even this value stress value also will go on decreasing, and ultimately at some point of time it will come and it will break. So, that will be fracture point. Now, that is basically known as the engineering stress engineering strain curve, while when you say now what we see that in this case you are assuming that you are calculating the value of stress and strain based on the actual area, original area A naught. Now, what happens, as we have seen that when there is permanent deformation, then the area will no longer be remaining constant. So, in this case what happens so this way it will move. So, this is known as true stress and true strain. If you take actually the value of the stress and strain, which will be depending upon the instantaneous area, so that is known as true stress true strain curve. So, you represent it as sigma and epsilon, and this if you look at this, it will be similar to that going into the this yield point region. So, maybe to the proportional limit it will come as similar one, but after that what you see is that this value does not decrease, as in the case of in this it will go on decreasing. However, in this case it does not decrease in fact, and it goes on increasing till the fracture point. So, that is the basically difference between the true stress and true strain curve. What you see that this zone, this is the stress value is going on increasing. So, it is basically increasing continuously. In fact, that is known as the strain hardening of the material taking place. So, this way what we feel that, so in this case this is the region where the hardening is completing, and that is what one of the mechanism is there, that is strain hardening. So, strain hardening is taking place in this region. So, so what we see, we can see that in plastic deformation it can occur in tensile, compressive or torsional loads. Now, load elongation or true stress true strain curve is plotted to study the deformation behavior. So, we have already seen that you just can study the deformation behavior by studying the load elongation or true stress true strain curve. So, as you see that true stress will be the load divided by instantaneous area. So, P upon A I, that is instantaneous area. Similarly, true strain is also defined as integral of dl by L. So, that is L naught to L. So, it is the original length and is the final length. So, that way your true strain values are calculated. Now, many a times you have different type of relationships which talk about the relationship between true stress and true strain, and you have the power relations also available, that is sigma equal to k epsilon n. So, that talks about the so k is the strength coefficient and n is the strain hardening exponent. So, this is this is known as power law and power relationship, and here k is known as the strength coefficient, and you will have n as the strain hardening exponent. So, for steel its value is something like 0.15. Now, even for the strain rate parameter also you have another relationship, and for that also you have a separate relation. So, that we can study later. Now, we will talk about the plastic deformation. So, what happens in the during the plastic deformation, the crystalline order is not lost even though some imperfections are introduced, and atomic movements are such that the crystal structure remains the same and after the plastic deformation. So, when the plastic deformation is taking place, as you have crystalline arrangement of, so atoms are arranged in certain order, and when there will be plastic deformation, then the crystalline order is basically not lost and certainly some imperfections may be introduced. So, basically if you talk about the mode of deformation, there are two modes of deformation, the slip and the twin. Now, how this slip and twins look like? So, in the case of slip, what happens that you have the arrangement of atoms. So, what you can see by the figure. So, in the case of slip, suppose you have atoms like this. So, you have, if there is arrangement of atoms like this, and then you have another arrangement like this way. So, now in the case of slip, there will be movement of the atoms from one side. So, it will be so before the slip or twin you will have the structure like this, but once there will be slip. So, what may happen is that your this one may go from here. So, your next will be from here. So, that way. So, this will be the example of slip. So, basically this is this is going to that position. So, from here it is going to this position. So, your next level will be like it will go like that. So, this is the example of slip. Now, in the case of twinning, what happens that in certain region so in the case of twin, what will happen that you will have the atoms arranged, and then you will have the movement of atoms will move like this. So, you have atoms here. So, you all these are so this is so in this zone. So, this type of mechanism is known as by twin. So, this is by slip and this is by twin. Now, this is the twinned zone, and what you see that in the case of slip, before or after slip, the arrangement of atoms, the way they are, the orientation does not change, whereas in the twinned zone you have the orientation is changing. So, that is the in slip you have steps created at the surface of the crystal. However, there will be orientation of the parts of the crystal remaining the same before and after the slip. In the case of twinning, you have the orientation changes of twinned parts as we see, and but the movement is only a fraction of the interatomic distance, whereas in that it may be few of the atoms there may be slipping. So, that is the difference between the slipping and twinning. The slip mode will be more common to ambient and elevated temperature, and at lower temperature in many cases the mode will be changing to the twinning. Now, if you talk about a deformed crystal and if you look at the surface of the crystal and if you see under the microscope, then you will be showing the parallel lines. Now, these lines are known as the slip lines, and these lines will be indicating that the shearing of atomic planes within crystal with respect to one another, resulting in the surface steps. So, you will have those formations. These slip planes which we find, so we will have the concept about how this deformation should be studied. So, we know that these slip planes are the closest packed planes in the crystal, and also the direction along which the slip occurs, they are the closest packed directions. So, the plane of the greatest atomic density having highest number of atoms per unit area, they are the most widely spaced planes, and also you will have the direction of greatest linear atomic density, that is close packed directions have smallest translation distance from one minimum energy position to the next. So, these are basically the traits of the slip type of deformation which occurs in the case of metals. Now, when if you talk about the ionic crystals, so basically energy point has to be kept into mind, and it is always seen that the ions of the same polarity, they should not be juxtaposed as nearest neighbors, because in that case there will be big increase in the potential energy. So, the slipping will be in such a manner that after the positive ion you will have a negative ion and then again positive ion, like that. The slip plane and the slip direction together, they constitute a slip system. So, basically if you talk about the slip system, so as we know that if you talk about one FCC system, so if your crystal is say FCC having a structure, in that case you have slip planes, as we know that you have slip planes of 1 1 1, and similarly you have a slip direction, so that is also that is 1 1 0. So, that way you have a combination of this slip plane and slip direction, they constitute the slip system. So, similarly for BCC system also you have 1 1 0 is the slip plane and 1 1 1 is the slip direction. So, that is more common, and also you have less common also slip planes like 1 1 2 or 1 2 3 or so. So, that also is available. Similarly is the case for even SCP materials. So, that way these they form these slip system. Now, what we need to study is that the stress at which this slip starts in crystal depends on the orientation of stress axis with respect to the slip plane and the slip direction. So, suppose if you talk about the plastic deformation, so if suppose you are applying the load along a tensile axis. So, suppose you apply the stress. So, if suppose this is the tensile axis and this is the stress. Now, if you talk about the one of the plane. So, if suppose this is your slip plane, so and this is the slip normal plane from normal plane here, and this is your slip direction. So, for such cases, if you look at, so you will have if you apply the tensile stress, so sigma. So, if this is the tensile stress applied. So, the shear stress, so resolved shear stress basically that is on a slip plane. So, resolved shear stress on slip plane. So, as we know that this is the slip plane and its normal basically is making angle phi 1 with this tensile axis, and this angle is phi 2. So, if phi 1 is the this normal making angle with the tensile axis and phi 2 is with the stress axis, in that case. So, in that case, so and no, phi 1 is that which is making with the stress axis, and slip direction is inclined at angle phi 2. In that case, if you take the resolved component, so that is shear stress, because the deformation is because of the shear. So, this will be basically component of cos phi 1 and cos phi 2. And the critical resolved shear stress value basically you require this shear stress value to reach some critical value and to start the deformation. So, that value is known as the critical resolved shear stress. So, if you come to the presentation here. So, the stress at which slip starts in crystal depends on the relative orientation of stress axis with respect to slip plane and slip direction. So, what we have seen that we have different planes at inclined at different angles, and the deformation will start so the slip system in the crystal will not have the same resolved shear stress for a given tensile stress along the axis, and the deformation will be initiated first on that slip system for which the critical resolved shear stress is maximum, and so reaches the critical value first. So, that is basically the point that for whichever wherever this critical resolved shear stress will be maximum, the deformation will start there. Then also comes a point that many a times we see that we can also do the analysis, and we can see that how with the this stress required when there will be a slip in the in any system. So, for any slip, how there will be change in the potential energy, and how the shear stress will vary. So, assuming that to be a sinusoidal curve, because if it is moving from one to other and it is coming again in between the two atoms, the atom is taking its position. So, being that as the point, the final one. Now, it is also proved that if you take it as a sinusoidal type of curve, so the the value of tau will be a function of also the Burgers vector. Then you will have other interatomic distances into common, and from there it has it was seen that you can have an idea about the the stress required to move the dislocation. Now, and you have the shear strength of the crystal also, you can have that, but what we see that the ideally the strength which the material should have, it does not show that. So, normally it should be mu by 6 suppose. So, but in actual case it becomes that factor becomes more than 1000 or even thousandth. So, 20 up to 20,000 or so or even more. So, that reason is because of the presence of dislocations, and also there has been studies on that showing that when we talk about the whiskers or where the dislocation is not there, in that case the strength is quite high, and once you induce dislocation then the strength becomes quite small. So, that way that is the concept of having the dislocation or the concept of plastic deformation, and that is what we will have we will study the mechanism by which you can see that there must be proper strengthening, so that the barrier to dislocation movement is there. So, we will be talking about different mechanisms in our coming lectures. Thank you very much.